All right, so this is the lecture on urine and MIcturition, which is a fancy name for urination. This should be a pretty quick one, but we do need to cover this material here. So the composition of your urine. I think a lot of this is kind of self-explanatory in terms of maybe color and odor, but basically all shades of yellow could be normal for your urine. Usually you don't want it too light because that means you're overhydrated, but you also don't want it too dark, which means you're dehydrated. So they always say like a straw color. If it is too light in terms of like clear, that's not healthy. And same with maybe like a really dark yellow, almost a brown. The appearance is produced by urochrome, which is a pigment produced by the hemoglobin breakdown. Diet, diseases, vitamins can all turn your urine different colors. So usually yellow is normal, but urine can be pinks, greens, any of that stuff, just depending on diet and what you've ingested. It should be clear, but it could be slightly cloudy, especially if your urine is very concentrated, like that first morning urination. Also, if you have like a UTI and bacterial growth in there, it could be cloudy as well. Obviously, UTIs aren't normal. The odor is affected by bacterial activity, also ammonia. So remember that ammonia is a waste that's excreted in urine and has very distinct scent. People with diabetes who have a lot of ketones in their bloodstream and then those filter out in the kidneys maybe have kind of a sweet smell to their urine. Specific gravity is what we call density, and we compare this to distilled water, which is 1.000 grams per milliliter. And normal would be 1.001 to 1.028, which means that your urine should be a little bit more dense than that of distilled water. And why? That's because of all those solutes that are in your urine. So it's very close to that of distilled water because urine is mostly made up of water, but you do have solutes, which will add a little bit of density in there. So the higher the specific gravity, the more dehydrated or the more solutes you might be putting into your urine, the more concentrated the urine. If we take the last two digits of the specific gravity, times it by a constant, which is 2.6, and that constant comes from matter per liter, and it's just a constant. It's always 2.6. But if you take the last two digits of specific gravity times 2.6, you get grams per liter of solid matter. So if you were to collect all of your urine for an entire liter and then dehydrate the water out of that urine, the solutes that are left over as dried matter, you could weigh those. Excuse me. And per liter, normal is 65 grams. So if you were to weigh all those solutes, you would get about 65 grams per liter in somebody with a specific gravity of 1.025, for example, which is pretty normal. Osmolarity, we've been talking a lot about that. That's the amount of salt, we just call it saltiness, osmolarity, like sodium, potassium, those types of things. Your osmolarity is going to be lower if it's more hydrated, right? So it kind of goes hand in hand with specific gravity. So if your specific gravity is high, your osmolarity is probably also high because you have more solutes in that urine. Normal is 50 to 1200, blood is 300. And urine can be either hypotonic or hypertonic to blood, just depending on your hydration status, right? You could be under 300 or you could be over 300. Typically, people, I would say, are over 300. The pH is mildly acidic. We've been talking about that. So it's from the hydrogen ions that are secreted in the urine as well as other metabolic acids. But the range is from 4.5 to 8.2, which means that your urine could even be slightly basic, but normal would be slightly acidic at 6. Remember, neutral is 7. Your urine is 95% water, 5% solutes on average, right? And we've talked about that as well. Urea is the most abundant solute. That is constantly, remember from the nephron, urea is constantly secreted and reabsorbed by the tubule throughout the nephron loop and also the collecting duct. Let's see here. Oh, other things that are going to be in your urine, other solutes. You're going to have salt, potassium salt, sodium salt, creatinine, which is a byproduct of creatine. Remember, none of that is reabsorbed, so it should all be in your urine. Uric acid, phosphates, sulfates, calcium, magnesium, the list goes on. Remember that urobilin is a breakdown product of hemoglobin. Remember, hemoglobin breakdown products can be excreted in the digestive tract or the kidneys. In this case, we're talking about it in the kidneys. We urinate about 1 to 2 liters of urine per day on average, right? It's called polyuria, so excessive urination if it's over that, oliguria, which would be under that, and then anuria, which would be kind of the absence of urine or very, 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 very small amounts of urine. And the amount of urine that you excrete depends a lot upon the chemical composition of your urine, your diet, but also how healthy your kidneys are. So somebody who has kidney failure will urinate a lot less, if at all. If they're waiting for a transplant, they're probably not urinating at all. Most of the time they go through dialysis, and that's the complete filtration of their bloodstream with no urine as a byproduct of that. Now, the less urine you produce, the more waste's build up, right? And so somebody with kidney failure who hasn't started dialysis yet has a large amount of waste in their bloodstream. And that can be very toxic to the body. It can affect the pH of the bloodstream, right? Because if it's not going to be excreted in the kidney tubules, then it's going to go back into the bloodstream and be circulated. It goes up to the brain. It can affect your mental status. It can affect a lot of different processes in the body. A couple diseases for you that your book goes over in section 23.6b. Diabetes. We talked a lot about diabetes. You know that diabetes is the excessive glucose in the bloodstream, but there are different types of diabetes. We have diabetes mellitus type 1, type 2. So type 1 is what you're born with. Type 2 might be what you're diagnosed with later in life, dependent upon obesity and things like that. But also pregnant women can get diabetes, which is just gestational diabetes. And then there's this one called diabetes insipidus, and that's actually a hormone imbalance. But essentially, we have chronic polyuria, which is the excessive urination, and that's due to high glucose in the tubule. So if you have lots of glucose in your tubule, you're also going to attract a lot of water, and therefore that will increase your urine volume and increase your urination, right? For diabetes insipidus, that is actually a problem with the pituitary gland. So ADH, antidiuretic hormone, is secreted by the posterior pituitary, and it's when it's not secreted in enough amounts. So antidiuretic hormone, remember, retains water and salt to increase your blood volume and blood pressure. But if we don't secrete that in large enough amounts, that water and salt is just going to be excreted in the kidneys, out in urine. So your collecting duct specifically is not reabsorbing that water, and therefore you're losing that. So excessive urination that way, really easy to get dehydrated that way as well. For those of you who have been around folks maybe that take a water pill, a diuretic, those work also on the nephron. So that is a chemical that induces increased urine volume. Excuse me. So grandma takes a pill that makes her have to go to the bathroom every 2 hours, right? A lot of people who have edema take diuretics or fluid on their lungs or fluid around their heart or something like that, right? Because that fluid is building up in that interstitial space, that tissue space around those organs, in the arm, in the foot, wherever edema is found. And diuretics increase urine volume by inhibiting the reabsorption of sodium and potassium and chloride, right? If we absorb that potassium, sodium, and chloride, now our medulla becomes more salty, our bloodstream becomes more salty, and the more volume we have in our bloodstream, if blood pressure is high, that fluid will go into the interstitial space and cause swelling. So what it does is allows sodium, potassium, chloride to remain in the tubule, in that nephron loop, and water stays then for the most part, and then you excrete urine quite frequently. That's going to be more than 1 to 2 liters a day. Caffeine acts as a diuretic as well. So maybe you're familiar with this, if you drink a lot of coffee, energy drinks, that type of stuff, you may have to go to the bathroom a lot. That dilates the afferent arteriole. And we know that caffeine dilates all of our arteries of our body, right? Because caffeine increases blood pressure. And so we need to dilate all of our arteries of our body to lower that blood pressure, but that also increases the amount of blood that can flow. And so if we dilate our afferent arteriole in our kidney, for example, what happens to GFR? It's going to go up, right? And if it goes up, then we're going to pass more urine, more filtration through that tubular system. And that's with super high levels of caffeine. Renal autoregulation will take over. And so with moderate amounts of coffee, you shouldn't see too much of a change in urination. Maybe initially you will produce a lot of urine after you drink that coffee, but ultimately it should not remain dilated like all day or anything like that. Alcohol, we talk about alcohol being a dehydrator, right? Or diuretic, but it specifically acts on the pituitary to inhibit ADH secretion. So antidiuretic hormone, anti-urination, right? So we are going to actually hang on to the water in the collecting duct. It's not going to let it out. It's going to hang on to it. And in that case, that will increase our urine volume and decrease our blood volume, which will dehydrate us. I talked about the diuretic of Lasix is the most common. So if anybody ever says they're on a water pill, it's very likely that it's Lasix. Okay, so let's just get into the process of urination. So micturition. Let's go back to review the urinary systems here, the lower urinary systems of the male and female. So here's female. Here's the trigone, which are the ureters, right? Coming down from the kidneys, filling this bladder from bottom to top. And here's the urethra. Females don't have an internal urethral sphincter, males do, but we do have an external urethral sphincter, and that is controlled by our pelvic floor muscles, which are voluntary. Males, here's the trigone here. So we've got ureters filling from the bottom up. Males, your urethra is a lot longer than females. Here's the prostate gland. So this is the prostatic urethra, the part of the urethra that passes through the prostate. Here's your internal urethral sphincter that is under involuntary control. Here's your external urethral sphincter, which is controlled by pelvic floor muscles, just like the female, and that's under voluntary control. And then urine will enter here. So keep that in mind here for a second. So the bladder relies on stretch receptors as it fills. So kind of like stretch receptors anywhere else in the body, right? Stretch receptors in the arteries when blood pressure is too high will tell the heart to beat slower so that we don't have that excessive blood pressure against those walls of those vessels. But remember the detrusor muscle, which is this smooth muscle here. Okay, as this bladder fills, it's going to stretch. Okay, and that'll send nerve signals to our brain, telling us that our bladder's full and that we need to relieve ourselves, right? If the detrusor muscle is relaxed as the bladder fills, the sphincters have to remain closed. Imagine that if your sphincters were open, imagine if the detrusor relaxed and the sphincters relaxed, you would just empty urine as fast as it filled your bladder, right? So these sphincters have to be controlled by the sympathetic, the fight or flight nervous system. And the sympathetic nervous system is usually contracting things. And so these are going to contract. But there's an involuntary and voluntary component to micturition. So let's talk about the involuntary part. As your bladder fills to about 200 mils, those stretch receptors will begin to activate. And it's a reflex. And reflexes don't go all the way to the brain. They go to the spinal cord. And so you have afferent messages going to the spinal cord, which is the receptor, saying, hey, we're full or we're getting full. And so the spinal cord will kick a message out. And this is in males. Will kick a message out that will tell your detrusor to contract and then relax that internal urethral sphincter. So if your detrusor contracts and this sphincter relaxes, that involuntary urge fills your prostatic urethra with urine, right? And that's going to put pressure on this external urethral sphincter. Remember, this is under voluntary control though, so this is still constricted. But that initial involuntary response is that this bladder fills about 200 mils with urine, the detrusor muscle contracts, this relaxes, and urine begins to move through the prostatic urethra and stops. Okay, that's going to put pressure or like give you the urge to have to urinate. Females, we don't have that internal urethral sphincter. So it just goes straight down into this area, our urethra, and then we can relax that sphincter here on the voluntary portion. So here's a picture from your book. Here's a full urinary bladder. Here's step one. Stretch receptors are located in this detrusor muscle wall, and they're going to send a message to the spinal cord. And the short reflex goes from here to here and then back out. Okay, but there is a longer reflex that we're going to talk about next. So the short reflex goes here to the spinal cord, and interneuron is located there, and then we'll kick out a message here to that internal urethral sphincter and tell it to relax. That's involuntary. That's in males, okay? For voluntary control, those same stretch receptors are going to send that signal, and part of that signal is going to go up actually to the brainstem and the cerebrum. And the cerebral cortex is going to come down and tell us to, if it's time to urinate, it'll tell us to relax our external urethral sphincter. Otherwise, if it's not time to urinate, it will tell it to remain constricted. Okay, so again, stretch receptors signal the brainstem, and efferent signals contract our detrusor and relax our internal. Okay, that's here. That same thing happens. And then depending on if it's time to urinate or not, because this is under voluntary control, this signal coming down from the brain will tell us to either keep this constricted or relax it if it's time to void. Okay. So that would be like in your female. Females would go through the voluntary action primarily, and so this detrusor would contract, and then that, excuse me, let's back up. So this would fill. The stretch receptors here would send a message up to your brain. Your brain would tell or send a message back down telling your detrusor to contract, but then depending on if it was time to void or not, to either relax or keep this constricted, right? The more the bladder fills, the more intense the signals get. And so if you hold your urine at 200 mils, that's fine. But as you get up to 400, 500 mils of urine, these contractions are going to be a lot more intense, and it's going to be harder to keep this urethra constricted. All right. So that's just kind of a quick little lecture on urine composition and micturition. Make sure you go over the objectives and read through the book.